We switch to the next session, to the last session of today, Corrosion in Concrete and Porous Media, chaired by Professor Dr. David Bastidas. Dr. Bastidas is professor in the Department of Chemical, Biomolecular and Corrosion Engineering at the University of Akron in the United States. His scientific research focuses on corrosion and materials degradation, including corrosion of steel in concrete, corrosion in novel geopolymers, smart corrosion, inhibitors, stress corrosion, crackling, localized corrosion, atmospheric corrosion, and galvanic corrosion. Thank you very much, Professor, for chairing this last session of today. The floor is yours.
Thank you, Therick, for kind introduction and everyone for attending. I'll try to keep the session very straightforward since we're running out of time and a little bit late. Sorry about that to everyone. So with no more hesitation, I will introduce Professor Carmen Andrade. She is a good colleague of mine and very well known in the corrosion of the steel and concrete world. And again, thank you, Carmen, for accepting this invitation. She is now an International Center for Numerical Methods in Engineering at the Politècnica University in Catalonia, at Barcelona. So Carmen, please, floor is you. Thank you.
Thank you very much, David, for that invitation. I am going to talk about generic relation between the degree of saturation of concrete resistivity and corrosion rate. That are some of the basic topics in the area. I think that a lot of people knows that corrosion of steel in concrete is producing an increase in interest due to the economical consequences and the lack of cheap solutions. And in spite of a huge amount of papers in the subject, there are many unknown aspects, and some of them remain completely empirical. And one of the things that we need more information is about the real weathering of the structures in the real conditions, because we have a lot of data on laboratory and very few in the real cases. This I show is a collapse that happened 2 years ago in one of the harbors of Spain when 500 people were dancing over. Fortunately, there were not fatalities. Well, this is the list of contents that I am going to address, the background, but mainly I concentrate today on the electrochemical techniques and the critical aspect to quantify the corrosion and the influence of the degree of saturation, which values of corrosion rate are the normal in concrete, the influencing parameters, and also a summary of the work we did just measuring in outdoor conditions and the equivalent Porous model that we developed, and finally the generic relations that we found. Well, first, coming back, it has to be mentioned that it was in the 60s or 70s that Purvé and Gouda, Montfort, Baumel, Engel, Ketche, these pioneer people, they were studying the corrosion. It's not new, in spite there are a lot of young people just dealing with now. It comes very, very old. And very good papers at that moment. They were studied at the beginning through the polarization curves, either potentiodynamic or galvanostatic or potentiostatic, in order to know which are the concentration of chloride that could develop corrosion. In my thesis, I was addressing the application of the linear polarization of the polarization resistance, and there I can mention Feliu and Gonzalez, that they were masters also from David Bastidas, that they suggested to me to try to apply this to concrete. This is the galvanostat, a handmade galvanostat that we did for just making the experiments. I used 2 meters long pre-stressed steels. I used one bar or one wire for working and the other for counter. And I was applying galvanostatic pulses in order to look whether it's linear or not the response. In that case, I was using different amount of currents and different times step waiting in order to realize whether it's or not linear. And it's quasi-linear really. And I was plotting the different RP's values, and we realized that they are very good correlating to the state of corrosion of the bars inside these beams, that some of them were made with calcium chloride. After we have extended to any kind of media, and also we developed a portable corrosion rate meter together with these people I mentioned before. We use a guard ring to confine the current inside a certain area in order to have very well delimited the area that we are polarizing there. And at that time, I was starting to apply this to concrete specimens or mortar specimens, changing the amount of water, because water aqueous corrosion needs water. In that case, the water was the change, and we realized that we have big changes when we just go to 100% relative humidity or partial immersion, and when we dry, the corrosion rate is smaller, and the same happens with the potential. And we stated that the kind of mechanism or the control of the corrosion in concrete, that it can be an activation control, but also mainly a resistance control. And this is very old back in the experiments. We did that in many cases with chlorides, with inhibitors, and we were able, together with Gonzalez, to be able to plot this graph that I show here, in which we present the corrosion rate versus the resistance of the mortar, the ohmic resistance. And we realized this resistance control that we were commenting. That is with several types of cements and several types of additions. And we were also just stating the levels of corrosion rate that you can find in function of the amount of water that you have in the concrete, and what is passive state. When we have less than 0.1 micron per square centimeter of corrosion, we can say that we are in passive state, or the corrosion is negligible because the concrete is dry. And the maximum corrosion rate we were able to measure is about 1 millimeter per square centimeter. And well, we ranked that, and we applied to this model, and we were establishing that when we are below this 0.1 micron per square centimeter, we can say that is negligible corrosion, because in 100 years there will not be almost any loss in the section of the steel. We rank to 0.5 micron per or 1 micron per square centimeter, and above 1 micron per we can consider very high the corrosion, because the time for having important loss in the diameter or the section of the bar is before these 50 years of service life that is the normal that we take into account for the buildings. And there, in that case, the ranking was made just based on this figure. But I realized later on that this is not enough, because all the data were laboratory data. What happens if we expose that to the atmosphere? As the values are the same, and yes, the values are the same ranking, but in any case, the effect of changing in natural conditions, the relative humidity and the water, is very different, the effect. I will try to summarize. We did big elements, and we made some holes in the elements, and we were measuring the relative humidity. We call it the internal relative humidity, because we just measure inside the concrete, of course in a small cavity, but in any case we measure the relative humidity not in the atmosphere but inside the concrete. We were measuring the corrosion rate with our portable corrosion rate meter, and we were following the potential and the corrosion rate, and we realized that it changes very much with the climate, with external conditions. And we were trying to analyze this further. The relative humidity that is parallel to these values are plotted here, and we realize that externally the humidity is lowering and going up, that we have the daily change in relative humidity, and the season change in relative humidity. But inside the concrete, the humidity, the relative humidity is much higher than what is externally. And this even in the very dry periods that we have in summer in Madrid. And when we were just comparing that with the temperature, we realized that the humidity is just moving opposite in a mirror manner with the relative humidity, with external relative humidity. And while the temperature inside and outside the concrete is very, very similar, the relative humidity, as I said, is completely different. In that case, it's much wet inside. This is not the first time that was published, because the people from Sweden, Fagerlund and other researchers, they were also studying that, and they have realized by other means this effect of a sponge of the concrete. The concrete retains the humidity much longer than when drying. And when we plotted the corrosion rate versus the relative humidity inside, we didn't find any relation. There is not a direct relation. Also with the temperature, I think that this is temperature and this is the relative humidity inside. In that case, there is not the relative humidity what is controlling, as in some cases there are people thinking. No, it's not the relative humidity what is controlling the corrosion rate. Well, we produce other kind of specimens, smaller, in order to handle them much better with this cavity where we measure inside the relative humidity, and we expose to different conditions inside the buildings or outside, protected from rain or just exposed to rain and also to the sun. This is a summary of 2 years of record. Now we have much longer record, and we were measuring in the atmosphere the stereo relative, the temperature, the stereo relative humidity, and also the raining regimes that we notice that is very key parameter for the relative humidity inside, the amount of rain that is just fed into the concrete. If we go what happens inside the concrete and we weight the specimens in order to have the amount of water that is retained in the concrete, we realize this following of the daily and also the seasonal changes, and shelter and non-shelter are very similar. Also the relative humidity inside is very similar in shelter conditions, that not exposed to rain, of those that are exposed to rain. But the weight is completely different. The weight in the case of the exposed to rain is much higher, and the changes are much higher than inside. Inside the concrete, if it is not raining directly, although the relative humidity is very similar to the outside, the amount of water that we have inside, liquid water, is much smaller. And just this is explained here, is much larger, exposed. And when we go to the corrosion, what happens with the corrosion? The corrosion is here, is that is exposed to rain and shelter. The corrosion potential is much noble, is lower. That means that it's not corrosion, active corrosion, while when exposed to rain is active values when we wet, because we wet sometimes artificially in this case. About the corrosion rate, again, in the protected specimen is no corrosion at all, is very, very low, the corrosion rate, while in the case of exposed to rain, I think that this is carbonated, the specimen, we are above 0.1, that is the threshold that I was commenting before. Sometimes that depends on the amount of water that is inside, and the resistivity is much higher, is 1 order of magnitude much higher if it is dry, of course, than it is wet. In that case, the corrosion parameters follow the effect. Here simply to show that when we are talking about the instantaneous corrosion rate, they changes a lot. But if we integrate in order to have the accumulated corrosion, it follows the typical to this diagram. I mean, the degree of damage is increasing depending on the seasons and the amount of rain, but it is continuously increasing the amount of loss of diameter here. And the interpretation, well, I have shown that, and it's known that the relative humidity daily follows a mirror performance with respect to the temperature. That is because relative humidity is relative to the total amount of humidity. I mean, what is the key parameter is the amount of vapor in a cubic meter of air. The relative humidity, it depends is how filled with vapor is that cubic meter, and that depends on temperature. In that case, when we lower temperature, we have a higher relative humidity and the opposite. But this is the cycle, the daily cycle about relative humidity. And in the case of the concrete, when we wet due to the raining, we have a gradient from the exterior to the interior. That means when it is raining, it takes 2 or 3 days, that in our case was 3 centimeters cover, 2 or 3 days or even longer, that this external water reaches by capillarity the bar. If it is raining and you measure immediately the corrosion rate, the bar is not noticing anything. You need to have a longer time for the liquid water to reach by capillarity the bar. If this raining is evaporated before has the time to reach the bar, a short rain is not influencing at all the corrosion of the bar, because there is this gradient that drying is longer and wetting is quicker because of the capillarity. But here is the summary. Inside the pores, there are 2 fluids. One is the vapor, the water vapor, and the other is the liquid water. And it has to be distinguished, the relative humidity, that is the amount of vapor in the atmosphere, from the degree of saturation or the volumetric fraction. And there is a gradient. In the interior is higher, the degree of saturation, and externally and internally they have the different relative humidity. And we had to produce this model in order that we call the equivalent pore model, in order to interpret what is happening in the cavity and in the pores of the concrete. If we imagine the capillary pores, because the gel pores, sometimes they don't exchange water, you need liquid water in order to just introduce water into the gel pores, but the capillary pores are those that exchange the water. And in the capillary pores, we have this layer of water, that the amount of water that is on the pores walls, and we have these 2 liquids, the vapor and the liquid water, that is exchanging by capillarity and by the raining. And in that case, we have this gradient that was well identified by our Swedish colleagues, and we interpret that in the bottom of the cavity, because we isolate the walls of the cavity and we have the change only here, we can say that the relative humidity here is the same that we have in the pore. And with that, we were able to interpret what happens, because we were able to try to follow what are the changes that we notice with the corrosion parameters. Well, one thing that is interesting is that inside the pore, if I increase the temperature and I am not in the surface, the relative humidity increases because the liquid water evaporates. And during that is in the morning, increasing the temperature until the mid-time, and during the afternoon, the temperature decreases. In that case, I condensate. In that case, during the temperature increase, there is a decrease of the saturation degree, and during the lowering of the temperature, there is a condensation. And this is a complete cycle that is daily cycle and also seasonal cycle. And this is again the daily cycles exterior that are here interpreted day and night, but inside the concrete happens that one that is different, because when we increase temperature, we increase relative humidity, we don't decrease, because there is not the relation to the exterior, and so in that case inside the concrete is reversed that what happens outside in the atmosphere. We plotted what is called the retention curves, that is mean the degree of saturation versus the relative humidity, and they are theoretical isotherms, but as we are not isothermal, but we are in completely non-steady state change, what happens inside the concrete is shadow here, because we go from low temperatures to high temperatures, and in that case, this is more or less what happens inside, and we can frame them with the theoretical isotherms, but we don't have an isothermal process. We have a non-isothermal process. In that case, temperature is a key parameter when we have concrete in the open atmosphere. And this has been plotted and studied by our colleagues with atmospheric corrosion. When you increase the temperature, you have evaporation, and after some time there is a decrease because you have evaporated completely the the water. In that case, at the beginning of increases temperature, there is an increase of the corrosion rate, but after there is a decrease. And that is why it is so complex to interpret what is happening here, because we have the skin and the interior, and this is a continuous opposite process that difficults very much the modeling. And well, we try to plot the relation between corrosion rate and amount of water inside, and there are trends with a normal, I say, scatter, because there are different temperatures, and also the differences between the skin and the interior. And the resistivity is the opposite. I mean, the resistivity decreases, of course, when you increase the amount of water inside the concrete. And with these values, we plotted again our graph corrosion rate resistivity, and we found that the trend is clear, although there is a big scatter. And of course, if the steel is passive, I mean, it's not in active condition, this is almost much more flat, because the corrosion rate does not go above 0.1. In that case, this is clear for active corrosion, but not for passive state. And why the scatter? Again, because we measure resistivity in the whole volume, while the corrosion rate is just near the bar. In that case, has to be an average of the resistivity that is not the average that we measure in the bar. In any case, we have this equation that we derive from the previous lab experiments, and that is confirmed, we think, after many years of measuring. And as conclusion, the relative humidity is not the same than the volumetric fraction of the saturation degree. There are two different fluids inside the concrete, and therefore the corrosion rate is not a function of the relative humidity. The temperature has two opposite effects: increase the corrosion rate, but as it evaporates the water, decreases the corrosion rate. And it depends in which moment and how fast the temperature changes that you can have one or other opposite effect. The rain has a crucial effect in the saturation degree, and with the same relative humidity, there are several saturation degrees. The corrosion rate and the resistivity have an opposite trend, and there is a resistance control in the concrete. And from this moment, we have these empirical relations, and that you can express the corrosion rate in function of the resistivity, but also in function of the volumetric fraction. And it can be linear or exponential. Both have bad correlation factor, but in any case, a correlation, and the same between the resistivity and the saturation degree of the volumetric fraction. The key point is that we are out of equilibrium, and it remains to be solved a generalization of this effect. Thank you very much for your attention.
Thank you so much, Carmen, for a beautiful and comprehensive presentation. I don't see any questions on the Q&A, so if anyone wants to raise a question, I think we have room for one question at least. If not, I'll ask you questions. So as a summary, what is then the worst scenario? Having the structure fully immersed partially immersed, exposed to atmospheric corrosion, or buried like in a soil? What can you elaborate on this?
Yeah, well, the worst is to have a certain time of raining, or that is saturation, and after just increase in temperature, that is typical in the continental climates in spring or autumn. Mainly spring, the highest corrosion rate are in spring. In winter, we have less corrosion rate because the general temperature is lower. And although you have more water, the temperature is lower. But as soon as you have the wetness of the winter and starts the spring, the corrosion rate increases a lot. And with submerged conditions, fully saturation is the worst. But if you have a limited amount of oxygen, in that case, you can detect less corrosion rate, but it's because you have less surface area corroding, because it's not the oxygen, but if you have less amount of oxygen, you have a smaller corrosion rate, but it's apparent, simply apparent. Locally, you may have a high corrosion rate in submerged conditions.
Okay. What about wet and dry cycles? Since
Oh, that is wonderful for the corrosion. I mean,
they promote the crystallization of the product.
Yeah. When you have water and dry and high temperatures, for instance, the Caribbean, that high relative humidity and raining, that is corrosion rate that are very high. And I can say that I was commenting with my Nordic colleagues. They thought that in Spain we have higher corrosion rates, but no, they have higher because their time of wetness during the year of their concrete is longer, much longer than in the southern countries in Europe. In that case, the average corrosion rate in the Nordic countries, in spite that they lower average temperature, is higher than ours in the southern part of Europe.
Okay, thank you so much, Carmen, again, and a big applause.
Yeah, thank you for you.
Yeah, let's try to move now to our next speaker. Will be Professor Ueli Angst from Federal Institute of Technology in Zürich, Switzerland. So thank you so much, Ueli, for accepting our invitation, and the floor is yours. Thank you.
Thank you, David. So it's really a pleasure to give this talk today on a topic of corrosion of steel in porous media, in particular on the role of the interfacial zone. Let me start by highlighting the difference of steel in an electrolyte and steel in a porous medium. If steel corrodes in an electrolyte, you are very well aware of different processes that occur, such as the dissolution of iron from the metal into the electrolyte, where ferrous ions are formed. These ferrous ions may then be transported away by different mechanisms, including diffusion, migration, or advection, and then they may also be oxidized to the ferric state. And when they are in the electrolyte, these ferrous and ferric ions may also meet other species shown in yellow here, such as oxygen, dissolved oxygen, chloride, or hydroxyl ions. And when they meet, they may form complexes or compounds, including some sparingly soluble compounds that may then precipitate. Now, if we are in a porous medium, we have a range of very similar processes occurring, but those processes can only occur again in the liquid phase. So it's the same reactions and transport processes occurring here in the liquid phase. But the difference now is that the metal is not only in contact with the liquid, but it is also in contact with solid phases and with pore space that may be air-filled, so that we don't have a bulk liquid electrolyte in contact with the metal there, but perhaps only some adsorbed layers of water molecules present on the surface of the metal. Now, this has major implications for understanding corrosion of steel in concrete, and some of those points that I will make today in my presentation have already been touched upon by the previous presentation of Carmen. But I would like to first talk about corrosion of steel in chloride-induced or in chloride exposure environments. And then in my second part of the presentation, I will talk about carbonation-induced corrosion of steel and concrete. So when it comes to initiation of corrosion in concrete in the presence of chlorides, it is very well known from previous studies, such as the famous work by Hausmann, who revealed a critical chloride hydroxyl ion ratio, or the work from other important researchers in the 70s, that we have this ratio, chloride hydroxyl ions, which is important for the tolerable amount of chlorides in the solution before we get corrosion. So we can see here in this log-log plot that we can tolerate more chlorides when we have a higher pH. And we were wondering if this concept, which is valid for steel in electrolytes, steel in solutions, if this concept is also applicable to steel in concrete. So what we did is we took samples from engineering structures. You can see here reinforced concrete cores. These cores have a diameter of 150 millimeter. They contain a piece of reinforcing steel, which at the time of sampling was not corroding. And then those samples were exposed to cyclic wetting and drying in chloride solution in the laboratory until corrosion initiated, which allowed to determine the chloride threshold value or critical chloride content, or however it is called, here abbreviated with C-crit. At that point in time, we also measured the pH of the concrete at the depth of the rebar by using a method that Alberto Sagüez and colleagues proposed in the 90s, which essentially consists in drilling a small hole into the concrete, adding an electrolyte, for instance, distilled water, and then after a certain equilibration time, measuring the pH in that liquid. So when we now compare the critical chloride concentrations from these cores that are taken from 120 cores taken from about 10 different structures, and we compare the pH and the critical chloride concentration, this is the type of result we can get. So you can see here the critical chloride content versus the pH, and you can see that we basically do not find such a generally applicable relationship as in the case of an electrolyte. But the different colors here in this plot represent cores taken from different structures. And if you look at, for instance, the yellow ones, we can imagine that we have in this yellow structure such a relationship present. So when we increase the pH, we can also increase the critical chloride content. But for other structures, this doesn't hold at all. And if we take all structures together, we cannot see any relationship, systematic relationship in this case. In fact, for a pH of 13, there is a huge scatter in critical chloride content here in these samples taken from structures. So we conclude that the pH is a poor indicator or predictor for corrosion initiation, chloride-induced corrosion initiation for steel and concrete, because the concept that is valid in an electrolyte seems not to be applicable in concrete, and that must mean that other parameters, in addition to pH, play a more dominant role in controlling corrosion initiation. We attribute this to the complexity of the steel-concrete interface. This sketch here stems from an international committee, RILEM Technical Committee, that looked into the steel-concrete interface in the couple of last years. You can see the schematic sketch here that shows on the left-hand side the steel part of the interfacial zone, and on the right side the concrete part of this interfacial zone. And you can see considerable heterogeneity along this interfacial zone. So the steel may be covered with mill-scale or native rust layers, which may also be cracked. Then we may have regions due to geometry where we have bleed or settlement zones, where we could have macroscopic voids in the concrete, interfacial voids. We can also have entrapped air voids, for instance, or cracks, and all these macroscopic voids may be water-filled or not, so they may just be partially filled, as I mentioned before, and that, of course, can be important. I would now like to only focus on two selected aspects of the steel-concrete interface. First of all, on the influence of mill-scale and pre-existing rust layers, and secondly, on the effect of entrapped air voids at the interface. So when it comes to the effect of mill scale and rust layers, in that RILAM committee, we looked at different literature studies that reported data on the effect of mill scale and rust layers, and we summarized that in the plot here on the left-hand side. So this plot basically is a normalized version of the different data reported in the different studies. We had to normalize these different data in order to allow for comparison between them. And what it means here is that a negative effect here means that mill scale or rust layers increase the susceptibility to corrosion. So they actually have a negative effect. A lower amount of chlorides would be tolerable if we are in this yellow area here. With the exception of 1 or 2 studies, there seems to be general agreement that the presence of mill scale and rust layers actually have a negative effect, which may be explained by a mechanism similar to crevice corrosion, which is a mechanism that Burkan, Isgor and colleagues, who will also present later after me today, proposed. And this is based on the mill scale being cracked and having crack and crevice-like geometries, so that actually corrosion initiation in that case may be due to a similar mechanism as crevice corrosion. Now, moving on to the effect of interfacial air voids, there is a lot of literature that indicated that corrosion in concrete tends to initiate preferably at interfacial air voids. And there is one very famous, well-known figure in the literature, which was produced by Andrade and colleagues in the year 2002, which shows that with an increasing amount of interfacial air voids, the chloride threshold value decreases. Now, one particular aspect of all these studies is that they were performed at a relatively high degree of pore saturation of the porous matrix that surrounds the steel. And when we look at conditions where we have a lower degree of saturation, we actually observe a slightly different case. And that brought us in this RILAM technical committee to the following hypothesis on the role of moisture in triggering corrosion of steel and concrete in the presence of chlorides. So you can see these different cases here. On the left hand, we have a case where such an interfacial void is fully saturated with water. And in that case, we believe it's reasonable to assume that corrosion would start here within the void. But if we have a case where this void is not filled with water, but basically filled with gas phase and only has some adsorbed water molecules on the surface, we find it is very unlikely to get substantial localized corrosion under these conditions, because it is very unlikely to form a pronounced macro cell, a pronounced galvanic cell with the adjacent cathodic areas, because the adsorbed layer of water has a very high ohmic resistance compared to the concrete beside, next to that void. So this in general reveals the importance of moisture and the degree of saturation exactly at the steel concrete interface in triggering chloride-induced corrosion of steel and concrete. Now I would like to move on and spend a few minutes on corrosion of steel in carbonated concrete, which is a very different process, but again also here the interfacial zone of the steel and concrete plays an important role. Steel in concrete is basically well known to be protected against corrosion because it is passive at very high pH. But when the concrete carbonates, the alkalinity is lost so that the pH actually decreases, and that may increase the risk of depassivation and then later on corrosion. This was very early also experimentally demonstrated in experiments in Japan. Hamada reported in 1968, but actually the experiments were done much earlier than that, so they are almost 100 years old, in fact, where steel bars or steel electrodes were immersed in different electrolytes that simulated concrete in alkaline condition, pH 12, or in an increasing degree of carbonation with increasingly lower pH values. And you can see the potential that was measured here over time clearly indicated that when we decrease the pH towards values in those simulated systems around 8, 9 or so, corrosion initiated. So we were wondering, again, in another Ryland Technical Committee, if this also is the case in concrete, and we looked at data from inspections of real structures, and all the structures that we considered in the evaluation were structures where the carbonation depth had exceeded the cover depth, which means that the steel that was inspected had been in carbonated concrete for quite some time at the time of inspection. Despite this, the majority of cases of those structures did not really show significant corrosion damage. In fact, all those blue areas here represent negligible corrosion damage, and only in about 10 to 15% of the inspected structures did we see relevant corrosion damage. So although the steel had been in carbonated concrete, in all these cases, there was not really relevant corrosion damage in the majority of cases. And when we further looked at these data, it was very clear that relevant corrosion damage only occurred when there was significant moisture exposure, such as issues with drainage, wrong drainage systems on facade elements or balcony slabs and so on, and in combination with low cover depth. So again, the moisture seems to be very important, and I think that also clearly became apparent from the talk that Carmen gave before me. And it is also well demonstrated in the literature that the instantaneous corrosion rate for steel in carbonated concrete increases when we increase the moisture condition. Now, in fact, there is a dramatic increase in instantaneous corrosion rate. And if we go from something of around 80% relative humidity to a condition where the concrete is in contact with liquid water, we increase the instantaneous corrosion rate by a factor of 5 to 10. So what controls the corrosion rate of steel in concrete? It's really the question, what is the really rate limiting step here? And again, if we rely back on an understanding of steel corrosion in electrolytes, then often one rate limiting factor is known to be oxygen diffusion here towards the metal surface, which is then represented by the oxygen diffusion limited current density. But when we try to, again, apply this concept to steel corrosion in concrete, we actually find that the oxygen limited diffusion current density is approximately 1 order of magnitude higher than the instantaneous corrosion rate. And these are results that were done in 2 different cement types, 3 different water binder ratios, and a broad range of different relative humidities. So it seems that the oxygen diffusion limitation is not really the controlling factor, which is the rate limiting step for corrosion of steel in carbonated concrete. So what else then can be used to describe and quantify here the corrosion rate in concrete as a function of the relative humidity or moisture state in general? And to understand that, there is the theory of a size effect, actually an area effect. Again, the steel is in contact with solid phases and with pore space, and some of the pore space may be filled with liquid and some not. And of course, if we increase the amount of surface where we have a bulk electrolyte present, liquid electrolyte present, we do that if we increase the degree of pore saturation, we can increase the area here. So that means an increase in electrochemically active surface area, and therefore also an increase in apparent macroscopic corrosion current density. This can be quantified by using the theory of capillary condensation, which is a theory that essentially relates the radius of stably water-filled pores to the relative humidity, and that can be used to quantify the electrochemically active surface area fraction. So it is the pore structure at the very interface, together with the exposure moisture condition, that determines this surface area on which corrosion occurs. And that is just an area effect that plays into the apparent overall corrosion current density. In addition to that, there is also an electrochemical effect because the pore structure influences the degree or the extent to which the ferrous ions in the electrolyte can move away, and that controls the concentration of Fe2+ here at the steel surface, which then has also an electrochemical effect on the corrosion kinetics. By utilizing this concept, it is possible to predict corrosion rates of steel in carbonated concrete very reliably, as you can see here, and actually also to predict corrosion rates of steel in other porous media, such as soil or wood. Now, let me conclude by saying that steel in porous media is, or corrosion of steel in porous media is complex because we have a complex interfacial zone. In addition to chemical influences of the electrolyte present at the metal, physical effects also play a role, in particular, the amount of water that is held in the pore system. So to better understand all of this, there is a need to better characterize the microstructure of this interfacial zone, and we have to consider the local, very pronounced local heterogeneities at the steel-concrete interface. With this, I am at the end of my presentation, and I would like to thank you for your kind attention.
Thank you so much, Ueli, for a beautiful presentation and all of those mechanisms inside. We all know that there's still a lot of work to do to disentangle all of these difference and a combination of the chloride and the carbonation. So I think now it's time for question and anything. Professor Romero Castaneda from Texas A&M has a question. So.
Yes, I have a question. Well, previous, but now the very nice presentation for Ueli. Thank you. So the question is regarding to your final statement or your final conclusion based on the oxygen and area. So you are mentioning that the oxygen, you didn't see that is a control step process. And also you mentioned that maybe, if I understand correctly, the area that is, I call it the active area, could be more influential in the corrosion rate. So is there any way that, or any mathematical tool that allows us to distinguish this or to have a pattern to make this distinction? Because that's very important.
Yes, thanks for asking this question. So the first part was related to the oxygen availability as being a limiting factor for corrosion of steel in concrete. And there, of course, you may think of situations where oxygen may in fact be limited, such as situations where we have extremely long submersion, but it takes decades to get the oxygen dissolved, the entrapped air dissolved in the water and to diffuse it out of the system. Unless there is an oxygen consumer in the system. So if you have an oxygen consumer, which could be any other electrochemical reaction, such as, for instance, the presence of sulfides in certain systems, or a strong pronounced corrosion that is a very effective oxygen consumer, in that conditions, you may get into oxygen limitations. But most concrete structures are atmospherically exposed, so they are not fully saturated and they have a huge amounts of oxygen reserve in the system, so that we don't believe that it really plays a major role in the majority of cases. Of course, there will be exceptions from that. And your second question about mathematical tools, as I mentioned, we believe that the theory of capillary condensation can be used to quantify the extent to which pores are filled and the extent to which the electrochemically active area at the steel can be quantified and then be related to the apparent corrosion current density that you can measure with any electrochemical techniques.
Thanks a lot. Thanks a lot for the question, for the answer.
Thanks, Ueli. I don't see any other questions, so I'm gonna try to get some comments. So as regard to the oxygen, I don't think oxygen exchange will be possible since you need a gradient of pressure. But of course, there are certain reactions that they are picking up oxygen. So any transformation of oxides to further oxidative species, and they are consuming oxygen. But what is very amazing and I think important is, according to your model on this pore distribution, void distribution, that might be something behind related to crevice. So can you elaborate that? Because my point is, why certain voids, certain geometrical distributions, they hinder the iron acid hydrolysis.
So you are referring to chloride-induced corrosion initiation when you talk about the voids in that case now, or?
Correct. Yeah. Pacific breakdown.
Okay. Yeah, there are a couple of different possible hypotheses. First of all, we believe, and with we I mean this RILAM technical committee that I mentioned, that the moisture state in the void is one of the most important parameters. I mean, obviously if the void is gas filled, you have at best some sort of atmospheric corrosion situation in there, which will never lead to pronounced pitting, which we can find in structures. If the void is saturated, then it's very likely to get corrosion because the pH buffer of the cementitious matrix is relatively far away. So you would need to, when you locally acidify the steel concrete interfacial zone, it's harder to buffer in such a void the pH, and that may likely give rise to corrosion. But in partially saturated voids, the situation is more complex because half of the void may be gas present, so we have supply of oxygen very close by, and the other half may be filled with liquid water, so that we can actually have electrochemical reactions going on there. And I think we believe it's an influence of both the moisture state, but also, of course, the geometry of the void and its chemical composition of the liquid phase in that void. But I'm not sure if crevice corrosion also plays a role there, because obviously if you have a crevice formed between steel and cementitious phases, that crevice interior will be well buffered at a high pH, unless the cementitious phases are carbonated. The situation is different when you have crevices in mill scale, because there we don't have any buffer in. I mean, we have it outside, but not in the crevice itself, or not at the wall of the crevice.
Okay. Before we move to next, final question from Carmen. So Carmen, you can go live and ask your question yourself.
I try to be quick. Is to comment on Homero's question that he was asking on the mathematical relation. We have an algorithm that connects the climate with the corrosion rate, but is empirical. But I think that we need to find mathematical expressions, but it's multi-parametric. The problem. And I sent a question to Ueli, is how he considers the temperature, because as I showed, the temperature is very critical in our results, and also about Kelvin, because Kelvin means the Kelvin application of the Kelvin equation is you need equilibrium, and we are out of equilibrium because of the temperature changes.
Yes, of course. The results that I showed were at constant temperature, but you're completely right that we don't have this in real exposure conditions, or at least in most cases. But I think you made very good points on the temperature during your presentation, Carmen. So there is no contradiction there between what you presented and what I presented.
Yeah, okay. It's only to remind you that don't forget about temperature.
Sure.
Thank you so much, Ueli. So big applause for you.
Thank you.
Thank you again for participating. Thank you so much. Okay, so let's move straight forward to our next speaker. Will be Professor Burkan Isgor from Oregon State. He's a well-known researcher and in corrosion of steel in concrete. And thank you again for accepting our invitation. And Burkan, let's go ahead and take the floor. Thank you.
Well, thanks everyone for attending. First, I want to apologize. I have a relatively slurry speech today. I had a dental operation yesterday. It's still healing, so I apologize about that in advance. Today, I'm going to talk about some of the recent advances in our understanding of chloride-induced depassivation in alkaline media. Now, the term recent here is loosely used. I'm actually going to cover a period of 15 years from now, but there will also be some very recent work that we have done in the last 5-6 years. As Carmen mentioned, corrosion of steel in concrete has been studied for decades. In 60s and 70s and 80s, there have been amazing work. 15 years ago, when I was a professor in Canada, I started an interest in looking at passivity and chloride induced passivation of steel in alkaline media. And with the recent or with the development of some novel or some advanced tools for nanoscale characterization techniques, we decided that we might have some opportunity to, explore some of the things that have not been studied before. And I have to acknowledge that at this about the same time as us, we also, there are other researchers that have looked at these things. So I want to acknowledge them, but today, most of the work is going to be based on my research group's work. I have to acknowledge that when you're presenting 15 years of work, you have to work with amazing people. And I have worked with amazing people, and I want to mention their contributions. There will be a lot of papers that will be covered here, and it's impossible to identify these people one by one. And the support started in Canada from NSERC and continued in NSF. I want to also mention their contributions. Now, again, this is the one we started 15 years ago to look at. The first thing we wanted to do is we want to actually look at the passive film. So we used TEM to do that. You can take an iron or carbon steel, create a pristine surface, put it in a simulated pore solution, concrete pore solution, high pH environment, and develop passive film over time. From time to time, you can take those specimens out in a nitrogen purge or argon purge environment, sputter some gold and tungsten on it, and then you can do focus ion beam milling to extract samples like this, cross sections. The idea here is to create electron transparent cross sections so that you can look at them from the side using TEM. The idea here is to see this thin passive film and characterize it if possible. So these FIB samples are about 100 nanometer thin. And if you look at those images, you can actually clearly see the passive film. This is a passive film that formed on steel surface after about 2 weeks of immersion in a simulated pore solution. The thickness shows here about 8 nanometers. This is actually thicker than the actual thickness because since you're looking at a 100 nanometer thick electron transparent sample, you're basically capturing the valleys and the hills that occur on the surface, actually here, sorry. And then the actual thickness seems a little bit wider. This actual, the thickness of the passive film that we found was about 3 to 5 nanometers. And you can characterize this further using TEM. If you look at the dark field images and you can tilt the sample to see what kind of images you're going to get, you actually see that the passive film is formed of nanocrystalline particles. And these are different angles of looking at the passive film. And, that shows us that there's a crystalline structure there. And if you look at the XPS data, and XPS is not done on those samples that I mentioned, FIB samples, but they're actually regular steel or iron surface. We have done both, and you basically create a pristine surface, develop the passive film again, and take the sample into an XPS, and then do XPS analysis. The horizontal axis here is the depth, which means that this end, which is 0, is the exposed surface of the passive film, and this end is the actual interface between the steel and the passive film. You can see that the red line clearly shows that the inner part, which is the interface between the iron and the oxide film or the passive film, has a Fe3 to Fe2 ratio of about 1. So there's a balanced structure that as you get closer to the outside surface, the Fe3 the percentage increases. So the outer side of the passive film seems to be more rich in Fe3 oxide, and inner side of the passive film is more rich in Fe2 oxides. And other people have shown this as well, so this is not necessarily new information. Now, our topic today is more about what happens to that passive film when you add chlorides. Now, we always talk about this critical chloride threshold concept, and theoretically, there is actually a reality to that. If you actually look at these things in, if you, for example, add chloride into that porous solution where you passivated those systems and you basically keep the chloride concentration low, you actually don't see damage on the passive film. But when you exceed that chloride content, a critical chloride content, you start actually seeing a damage on the passive film. So there is actual concept of critical chloride threshold. There is a big debate about whether, you know, how practical that is or whether it is useful or not. But theoretically, from theoretical discussions, we can say that there is actually critical chloride threshold. And if you look at the XPS data, you actually see something interesting happen when chlorides come into contact with the passive film. This is the XPS signature data. Horizontal axis shows binding energy. So there are the top line is basically the binding energy of at the surface. Basically, you can see that this binding energy, this peak here corresponds to an Fe3 oxide structure, and the bottom one is deeper inside the passive film, and this peak shows an Fe2 oxide structure. In between, you see a mixed system. So when you add chlorides, what happens is that the Fe3 to Fe2 oxide ratio at the deep inside the passive film, near the interface between the metal and the passive film, it doesn't change much, but you see that Fe3 concentration actually increases with the chloride addition. So this is also something that we have seen in other people's work as well. So Fe3 concentration, the Fe2 oxides basically become less dominant in the other surfaces as chloride increases. Now, again, up to here, what I showed you have been shown by many people, so it was more like a background. So when we talk about how chloride-induced depassivation occurs, there are different models that have been used to explain that process. I picked here two of those. There are more than two, but I picked here two because they capture more or less the big messages of different types of models. One is basically something we can classify under ion exchange model, where chloride can actually be absorbed and diffused into the passive film. And some people explain after diffusion how the breakdown occurs in a different way, and the others say that maybe it actually destroys the passive film. Some people show a different way of passive film destruction, but at the end of the day, this whole model is based on the implication that chlorides need to diffuse into the passive film. There is another approach in which the chlorides are not necessarily diffusing into the passive film, but actually creating some iron defects, iron vacancies, and those vacancies diffuse and create basically a defect structure at the metal and passive film interface. Again, testing these are difficult. At the time, again, this is a long time ago, we're talking about publications 2015, but the actual work was done much before that. We wanted to use some experimental techniques to see which one is more reasonable. Again, at that scale, you're very limited experimentally. So we tried to be innovative here. We use what we call a electrochemical quartz crystal nanobalance, EQCN technique. Basically, a quartz crystal is a material, piezoelectric material. When you pass a current through it, an AC current, it starts vibrating, and it vibrates at a certain frequency. And when if you actually change the mass of that crystal, you actually change the vibration frequency, and that means that the vibration frequency can be correlated to the mass change of the material, which is a very useful tool because you can do this in nanograms, in very, very, very small quantities. So we created this EQCN cell where we actually put on an quartz crystal in pure iron coating and expose it to a pore solution, or simulated pore solution, and we first passivated it. And when you see actually, when you passivate, you can see the OCP, open circuit potential, going into passive direction. You can also see that frequency of the quartz crystal decreasing, which is an indication that a mass gain is occurring, and this is an indication of passive film formation. Now, when you start adding chlorides, this is basically the data that I just showed you, this purple line here and OCP line here. At one point, when you start adding chlorides, you see something very interesting. There's a sharp slope change occurring in the frequency. And this this is actually corresponding to a mass increase. And at the time, we tried to interpret this, maybe overinterpret this, I have to admit, to what might be happening to the passive film. And this mass increase right after chloride addition and before any pitting starts, we actually interpret it as absorption of the chlorides on the surface of the passive film. Now, this paper was reviewed by three reviewers. One reviewer actually said that the reviewer agreed with us. The second reviewer said that that mass increase probably is due to corrosion product formation. We were able to show that that was not the case, but the third reviewer actually said that that mass increase is likely because of chloride ingress into the passive film. So you can see it even in one paper in a very simple, over-explained data, there were some controversy. At the end of the day, we were able to make all the reviewers happy by writing this sentence here. Another hypothesis for the gradual increase mass gain observed is absorption, possibly followed up by chloride ingress. But at the end of the day, I personally was not happy where we were. At the end of that work, these are about 2013, 2015, we actually had a idea, again, based on the literature. It's again, a lot of things that I'm showing on the slide are suggested from the 70s, 80s, where an oxide film, again, the form here is not important, but it is, we know there's more of an Fe3 type of structure. Chlorides can form these species and take the iron out, and these iron chloride compounds are generally not stable in the solution, so chlorides actually release into the solution and come back and do this work again. So there is this understanding at this stage, but we didn't know exactly how this process took place. At that point, again, this is coming to the recent part of what I'm presenting here. We decided that maybe we cannot go anywhere with experimental work anymore. So we thought that we have done everything we can do. And if the EQCN study that I showed you probably gave you a hint that we were actually stretching our boundaries a little bit. So we decided that maybe atomistic modeling could be helpful. Now, again, going into what atomistic modeling is and what these modeling tools do is a very big topic, which is pretty difficult to cover here. But we use reactive force field, molecular dynamics, and density functional theory to do this work. Reactive force field molecular dynamics is basically a simple, well, theoretically simple approach where you actually assume that the atoms interact with each other following Newton's second law. You have to define an acceleration based on a force field, and that force field has to be defined in different ways. You have to define some non-bonded energies and bonded energies, And with this approach, with molecular dynamics, you can model processes that involve bond formation and bond breaking, which are very relevant to the chloride-induced depassivation. And you can relatively, again, this is all relatively, simulate large domains where they might be represented spatially, the passive film. Temporally, time-wise, there are a lot of challenges here, which I'm not going to go into. DFT is a more first principles tool, which actually solves Schrödinger-like equations, very computational intensive. So that's why you cannot use very large domains. You ask surgical questions to DFT, like what is the absorption energy of chloride on the oxide surface? Or what is the energy required to insert chloride into an oxide? What is the energy to form an iron vacancy? Things like that, very surgical, very pointed question. And DFT can actually answer those things using advanced first principle approaches. Now, all of these questions we covered in different papers. I'm not going to go into those in detail, but I want to show some results, mainly from the molecular dynamics simulations. First of all, by simulating the passive film formation, we have actually shown that what we have shown experimentally using XPS was actually confirmed. By looking at the distances between the pairs of atoms or iron-oxygen atoms, we can actually look at what we call a pair distribution function, and the horizontal axis is basically the average distribution between different atoms here. You actually have these arrows showing the signature points where different types of oxides, and we actually see that the outer layers are mainly composed of Fe3 oxides. The inner layers are mainly composed of Fe2 oxides, and middle layers are a mixed bunch. This was a good confirmation. We started our research like that, but then we actually wanted to see what chlorides do to this passive film, and we added chlorides into the electrolyte and see what happens. Now, this is a very big topic to cover, which I'm not going to be able to do in this short presentation, but some big messages here is that a little chlorides don't do anything. So chloride content is important to initiate a process. The pH is important. How much OH you have in the electrolyte is important. That what Ueli mentioned, chloride to hydroxide ratio actually is very evidently shown in these simulations as a critical factor how process initiates. But when you have enough chlorides in the system, you actually can show that some of the, first of all, the process starts with some of the OH ions being absorbed on the surface, and near this the metal or film electrolyte interface, you actually get some acidification, and after that acidification, you start absorbing some chlorides. Now, this chloride compound is not dissociating from the passive film. This actually stays on the surface. It doesn't take a iron atom away, but as the time proceeds, you actually start forming iron chloride species, which can be taken out of the surface, and you actually start forming iron vacancies. And you can see that as you move these simulations, the iron vacancies start moving toward the metal oxide interface. Again, these simulations, as I said, are very time limited. We cannot do these simulations for very long periods. We're talking about very small time periods here. So we cannot show the defect formation at the steel at the metal passive film interface, but it gives us a hint that because these iron vacancies are moving in that direction, there is a suggestion that a model like point defect model might be the more appropriate way of describing this. And we did not see any chlorides penetrating into the passive film in these simulations. And As you look at the period distribution functions, you also confirm that shift from Fe2 to Fe3 structure as well, so which was also very useful. Now, this is the only slide from DFT. As I said, DFT is very good at answering surgical questions. Now, what we asked in the, and we asked many questions in DFT, but today I'm going to show you just this slide. We asked whether those 4 steps that I mentioned to you, this step where acidification or local acidification occurs, then some chlorides absorb some, and then some chloride compounds form and dissociate from the surface. Are they thermodynamically feasible? And DFT is very good at answering these kinds of questions. You can look at different things like, for example, reaction energies. A negative reaction energy means that the process is feasible. You can look at the bond lengths. The longer the bond length means the system is stretched longer. You can look at iron vacancy formation energies. You can see the lower the energy, the more tendency to iron for vacancies to form. So DFT simulations all confirm thermodynamically in a way that what I showed you in molecular dynamics simulations were also correct. Now, well, I shouldn't say correct, but they supported each other basically. Now the conclusions, atomistic simulations that we have carried out did not support the passivation models that require ingress of chlorides into the passive film. We actually showed that, or our simulations showed that chlorides remain either absorbed on the surface of the passive film, remain in the electrolyte, and catalyze the generation of iron vacancies in the oxide film. And when those iron chloride compounds go into the electrolyte, they actually, they're not stable. Chlorides come back and keep doing the same thing. So there's a catalytic process there. We actually showed a lot of things like the theoretical concept of chloride content, the role of pH, the role of chloride content, and at the end of the day, we were pretty happy with where we are. Now, I always get this question, why all this? Why do we need to study all these things? And I actually think it's a very valid question. I don't dismiss these questions. There is a practical aspect of corrosion research, and there is a scientific theoretical aspect of corrosion research. Personally, I always think that more science is good. More we can actually be useful practically. But there is, I think, a practical aspect of this as well. Understanding passivation and chloride-induced depassivation process in the atomic scale might be useful in the future for developing custom design corrosion inhibitors and corrosion resistant alloys. And our work is going in that direction. We're trying to work on those 2 aspects. So we're trying to get something practical out of this. So when you understand how chlorides work, maybe you can develop certain things to prevent those things, those processes. Maybe you can block some of the catalytic processes. So things like that might have some long-term practical implications. As I said, there were a lot of papers that covered this research that I present over 15 years, and I really appreciate your time and patience with me.
Thank you so much, Burkan, for beautiful and very complete presentation. Of course, more science makes you healthy, and I saw a lot of science in your presentation. You very well managed with all the thermodynamic transport and reaction, what makes good. And thank you for the mechanisms and the computer-aided results. So before I move to some of my comments, I'll let you take a Carmen question. Probably, Carmen, you can go ahead live and ask Burkan.
Thank you, David. Well, many thanks for your very interesting presentation, Burkan. My point is about the water molecule, because I didn't see it, and I think that it plays an important role.
Yeah, there is water molecules here, Carmen. Maybe I didn't show it, but you see the oxygen, hydrogen, the actual electrolyte is a water-based electrolyte.
Yeah, okay. In that case, you take into account. Sorry, because it was very quick on that. Well, I appreciate very much your presentation.
Okay,
thank you.
So I got some comments. First, I think I'd like to credit Professor D.B. McDonald for the point defect model. So we all know that he is the one, okay, the one and only, by the way. And point defect model is D.B. So we are now working on a different model because we are intrigued about the electrochemical activity coefficient. So can you elaborate a little bit on how to account for this on a DFT model and how to make the DFT model more dynamic process?
Well, doing kinetics with DFT is always a challenge because of the computational limitations. And I first of all, I have to acknowledge Professor McDonald as well. If I didn't say his name, it's my fault. Point effect model is definitely is something that he created, and I really think that he should be acknowledged. But a DFT question, studying kinetics is very challenging with DFT. You can do a lot of things, like you can actually look at activation energies, and you can look at those, take activation energies and relate them to kinetics. So there are ways of doing this. But looking at time scales is still a challenge with DFT. A lot of people have started working on dealing with these challenges, and especially the recent work on looking at inhibitors with DFT, etc., is showing that there is quite a bit of interest in looking at that. But I want to be on the cautious side about what DFT can and cannot do in a time-dependent fashion. I'm definitely one of the first people who will say that this is something that has a promise. But if you ask me whether we can do everything, my answer will be not yet, at least right now. But hopefully in the future we will have more tools to deal with that.
Okay, and about the idea on how to incorporate, account for the electrochemical activity coefficient, do you have any insights to guide people into that matter?
So again, electrochemical activity, it's a good question. Maybe it's indirectly happening here. The activity is considered indirectly, both, especially in the molecular dynamic simulations. But I have to think about, I'm going to be honest with you, I have to think about how activity is involved in these calculations. Probably there is some indirect incorporation of it, but explicitly we are not doing anything to incorporate activity to these. We are speeding, we are making the process a little bit faster in reactive dynamic, reactive force field dynamic, molecular dynamic calculations by applying an electrical potential that actually makes the process a little bit different. But if you're asking about the activity in the electrolyte, I have to think about that, David. I don't have a very good answer for you.
That's fine. So yeah, appreciate it, and maybe we can establish collaboration. Okay,
sure,
so
absolutely. It's an interesting question.
Big applause for you. Thank you.
Thank you.
Beautiful presentation, and I'd like to keep that level. You know, we're raising the bar, and that's good for everyone attending the conference. So our next speaker will be Ulises Martin. He's a PhD student of mine at Akron, and thank you again, Ulises, for participating, and please go ahead and take the floor.
First of all, thank you for giving me this opportunity. My name is Ulises Martin. I'm a PhD student at the University of Akron, and today I'm going to talk about the passive film evolution over 2.5 years of linear duplex stainless steel reinforcements embedded in mortar containing chlorides. For today's presentation, I will briefly introduce how the corrosion of reinforced concrete structure happens, also what are the compounds forming the passive film stainless steel and how that it's developed depending on different variables. To then go on the study that we carry on going from material and techniques to resultant discussions to end up with conclusions. So let's begin. So in order to explain how the corrosion-reform concrete structure happens, the 2D model shows there are three main stages. The initiation, which takes the longest of all three, where the chlorides and the oxygen that are inside the electrolyte will migrate to the concrete by mass transport till they reach the passive film, given to the activation process, which starts by depleting the passive film and ended up getting to the rebar. Once these aggressive agents reach the rebar, they will start forming some oxide scales, which have a higher volume ratio than the steel, adding some recrystallization pressure, which will exert some tensile stresses on concrete. As everyone knows, concrete works perfectly under compression, but not tension, inducing some cracking. After the first crack start, more chlorides and water can get inside the concrete more rapidly than just by mass transport through the concrete, and more oxidal scale can be formed, ended up by a huge tensile stress that by espallation will take out the concrete cover, and now our rebar is now exposed to the chlorides. So let's see now how this passive film is made on and how can we see the protectiveness of our stainless steel. So concrete, as we've seen, has a pH around 12.6, and based on the Purbeck diagram of iron, chromium, nickel elements at room temperature by Putamanek et al., we said the two main elements forming the chromium oxide and the spinel phase, which both are a p-type semiconductor, meaning that they tend to accept electrons, making the passive film less dope and increasing the corrosion protection. However, this passive film is not only formed by the chromium and the spinel phase, it also depends on the potential that we are, as we can see from the Moshotki plot combined with the CPP, where we have this relation that depending if we're in the cathodic, for more cathodic potential, we'll have the reduction of chromium oxide, we'll have the p-type semiconductor. However, as we get close to the E-core, we are reaching the N-type semiconductor, which are the iron oxide, which are semiconductors that tend to donate to make the passive film more dope and less protective. If we reach to the anodic potential, we start actually dissolving the spinel phase to then continue with this chromium layer, depleting even more the corrosion properties of our metal. As we can see in the image of the right, this exchange of electrons can be seen from the electrolyte, where the outer layer is mainly formed of the iron, which are the N-type, donating these electrons. However, towards the inside, in contact with the alloy, we have the chromium oxide, which are the p-type, and that give the passive film most of the corrosion protection properties. So by the Moshotki theory, if the potential that we have on our rebar, it's above the flat band potential, the passive film will have this double layer of the chromium and iron oxide having the p-type and n-type respectively. However, if we are below this flat band potential, only the chromium oxide will be formed. As we can see by this Auger study on the right, where they study the 304 alloy in concrete pore solution, we see that in fact the iron and nickel oxide are the ones on the outer surface, and the interface between the alloy and the passive film, it's mainly form of the chromium oxide. This is very interesting. However, most of the studies up to date are not with real concrete. Usually they have simulated, and they don't use either the rebar from construction materials, or the exposure times are very short. Hence, we decided to carry on a study with OPC Portland cement with 3 different stainless steel grades, 2 lean duplex, paying more attention to the 2001 lean duplex stainless steel, which has a very low nickel content, and subjected to a long exposure to 4 different chloride concentrations. As we see here, we have the 3 different alloy composition. We use some concrete mortar contaminated sample with 0, 0.22, and 4% weight chloride per weight of cement, where we applied some different electrochemical setting to see how this passive film was evolving and what the corrosion properties were. First of all, we had the Isgor and Akron monitoring of the 2.5 years of exposure. As we can see, we selected both extreme, the 0 and 4% weight of chloride. For the 0, we had the highest, most noble potential for all 3 alloys, stabilizing, reflecting in a lower unstable current densities. However, when the chlorides were added, this stabilization happened at lower potential, so more active, with a difference of about 100 to 80 millivolts different compared to the non-chloride, so the non-chlorine samples. This was also reflected in a higher current density. However, all 3 stainless steels were far below the limit for the low corrosion by the standard, which was 0.1 micrometer centimeter squared, showing the good protection over this long exposure time of all 3 stainless steels. By impedance, we saw a very similar trend with a 0 and 4 weight % of chlorides, where all the values were above the 100 kiloohm per centimeter squared, which showed that no passivity breakdown happened at any point for the 0 or 4% chloride. The slight difference between the 0 and 4 was that the 4% shows some small decrease after 2 years, a year and a half, compared to the 0, which only varied right at the end of the testing. All the impedance was fitted with the electric equivalent circuit seen here. We have 3 time constant, 1 resistant for the solution, 1 time constant for the mortar to take into account the porosity and the solution inside the concrete, and then the 2 typical one for stainless steel being the film and a double layer. With the equation with Mansfield and Brook, the effective capacitance of the film and double layer were able to be calculated. As it can be seen, most of the effective capacitance increase with the amount of chloride in the concrete, which then could be related to the passive film thickness by the equation here. Interesting enough, the lean duplex stainless steel showed the thickest values of the double layer, even on the 4 weight % chloride, when it has the lower nickel content. Following with the semiconductor properties, we saw that all 3 stainless steel show the 3 typical peaks that we previously presented, with the reduction of chromium oxide, the iron oxide, and then the oxidation of the spinel and chromium. The thing, more in-depth analysis of this more Schottky plot was seen by the flat band of the acceptor and the donors, as well as the carrier density of the same. It could be seen a similar trend with all 3 stainless steel, where the flat band of the acceptor, increased toward higher potential as time went through, which show that this higher potential meant that the chromium oxide was able to accept more electrons easier, meaning that with the passive film was growing this corrosion protection. However, the flat band for the donor part was becoming more and more negative, meaning that the iron was also able to donate these electron becoming more porous and more dope passive film. The carrier density for the acceptor and donor constantly increased with the chloride content, which it's seen on literature. However, the acceptor of the lean duplex was the lowest of all 3, showing its outstanding corrosion protection. Finally, we did some XPS analysis at the beginning of the testing and after 2.5 years. We saw that both lean duplex had an increase of 20% of the cationic fraction of the chromium compared to the only 10% of the 304, showing that towards this 2.5 years, this chromium layer was being increased and enhancing the protection, as we've seen by the Isgor and Akron monitoring, as well as being very stable passive film and protectiveness seen on the impedance. So as a summary, over these 2.5 years exposure of the concrete samples for our 3 different stainless steel, we saw that all 3 stainless steel were able to stand way below the 0.1 micron per centimeter square, proving their standing corrosion protection. We also saw that this duplex stainless steel was able to withstand the chloride amount and show that no passivity breakdown over these 2.5 years because of the 100 kilo ohm centimeter square towards the entire testing. Also that the lean duplex stainless steel, the 2001, was able to grow its chromium layer by a 20% compared to the only 10% of the austenitic stainless steel. And that by the flat pan potential, even though the donor was going towards more negative values, meaning that the iron layer was donating more electrons, the acceptor layer corresponding to the chromium was gaining, was increasing their potential, meaning that he was absorbing more electron and making a more stable and less dope passive film. Thank you for your time, and I'll be glad to answer any questions you may have. Thank you.
Thank you so much, Ulises, for precise presentation and staying attached to the time. So we have time for a couple of questions, and I will take any. So please go ahead and unmute yourself and ask.
Thanks, Ulises, very much for the presentation.
Thank you.
I lost, maybe you put, but I lost. Have you calculated the resistance of the film, the values of the resistance of the film? Because it looks that is very high in the stainless steel.
Yes, we calculated, I should have it on here. I didn't present on the presentation, but so these were the fitting parameters of all 3 stainless steel. So here we have the resistance of the film, always in the kilo ohm centimeter square for the 0 and 4% chloride, as well as of the Charles transfer resistance, which was of 2 to 3 order of magnitude higher. This order of magnitude was the same for both lean duplex stainless steel as well as the austenitic stainless steel. Okay, thanks. Because always I was wondering which could be the resistance of the film, and at least there you have an order of magnitude. Okay, thanks. Thank you. Thank you for the question.
So if that is the case, thank you again, Ulises.
Thank you, everyone.
And, now we'll shift our order. So we'll go first with Jacob, since this is a live presentation. We'll take Rutambara. The very last, this will be a pre-recorded session. Okay. Yeah. So let me introduce Jacob Red. He's a student of mine at Akron, and yep, he will be talking to you about some corrosion inhibitor, smart corrosion inhibitor. So thank you, Jacob, for participating, and go ahead, take the floor. Thank you.
All right, thank you everyone for having me here, and good evening, good afternoon. My name is Jacob Bress, and today I want to talk with you about my research in the pH-triggered release of sodium nitrite from novel California microcapsules in simulated concrete pore solution. So to give a brief background, as the corrosion of reinforced concrete is a major bane to cost and life, as in the 2000 Lowe's Motor Speedway Bridge accident that caused near 100 injuries. The the degradation of reinforced steel needs to be have a lot of research in it. And so in my research, we focus on the microencapsulation of corrosion inhibitors. And in this plot by Petiot et al., we can see the various forms of microencapsulation that have been used for corrosion inhibitors recently by a function of capacity, complexity, and cost. So in our journey to create a microcapsule that can be cost effective and scalable for the industrial scale, we've chosen solvent evaporation technique. Now, being able to use this microencapsulation, we can avoid the leaching of inhibitors in the concrete, as well as the premature binding of our inhibitors in the matrix and any other early reaction forms with a concrete matrix. Additionally, nitrite corrosion inhibitors are our inhibitors of choice, as they are one of the most well-known, the most widely used, and they are very effective. And what they do is they compete with the chlorides to form the passive Fe2O3 and ferric oxide layers and oxyhydroxide layers on the surface that can protect against further corrosion. To encapsulate these corrosion inhibitors, we wanted to use an environmentally friendly shell material. So in previous research by Panda et al., the colophony or pine resin has been able to be used for delivery of drugs in a simulated human body environment, as well as research by Canovas et al. Has shown that colophony pine resin itself can actually increase the mechanical properties of the concrete in terms of its compression and flexural forces. So colophony is formed of many different resin acids, but mostly composed of abiotic acid, which is shown here as this inset, about 90%, and it's very cost effective. So it's a good vehicle for our corrosion inhibitors in our reinforced concrete. So to begin, the synthesis of the microcapsules was done using the solvent evaporation technique, as is very cost effective, easily scalable, and rather simple. By dissolving our colophony in an organic solvent of ether, followed by stirring with the addition of our corrosion inhibitor aqueous mixture, and then finalizing with this double emulsion by adding an additional aqueous solution to form these shells here with smaller vehicles of the inhibitors encapsulated, as shown in the diagram. And here we see an SEM image of a single microcapsule formed by this method. And then in the end, the solvent was evaporated to form just the solid microcapsule shell. These were characterized using electrochemical measurements in the standard 3-electrode setup with using our carbon steel rebar that we purchased commercially, cut to expose just in delimiting the outside the outside riveted area as our working electrode, with a calomel reference electrode and graphite counter electrode. Our composition is shown, and we characterize this corrosion performance by potentiodynamic polarization and EIS. Right. In terms of the release for the microcapsule, the hypothesis was that because the colophony has a pK value of about 7.2, that the form of the abiotic acid will be in its protonated form at our pH values below this value, and it will be deprotonated at values pH values greater than 7.2. So to show this as the release mechanism dominant for causing the diffusion of our corrosion inhibitors from inside a microcapsule to outside, we tested with multiple pH solutions, including DI water, around pH 6.8, carbonate bicarbonate buffer of pH around 6.9, and a simulated concrete pore solution of calcium hydroxide saturated of pH 12.6. Just to show at the pH below, near, and far above the pKa value. After synthesizing microcapsules and imaging with SEM, we can see that they have diameters about around 87 to 90 microns in diameter, with a wide variation, which is well known for the solvent evaporation double emulsion technique, including some small pores on the outside edge. Now these pores will become more crucial when we get onto the release and some of the later slides on the effectiveness of the microcapsules. And here we see a close-up of a group of microcapsules, all spherical in nature with some dimples. And characterizing the microcapsules by FTIR to see the chemical bonding, we can see that after exposure to different pH solutions, 12.6, 9.1, 6.8, the previous solutions discussed, as well as just leaving in our synthesis solution, which is around near neutral, we see a change from our stock abiotic acid shown in our FTIR scan in black to the other spectra of the formation of additional carbon double bond to oxygen peaks, carboxyl peaks, and this is due to the known oxidation mechanism of the colophony shown by Ren et al. Now this can also be beneficial to our system, as it can show that the colophony not only can encapsulate these corrosion inhibitors, but also have an effect of scavenging some oxygen molecules as well. And as we see that in all of these solutions, we do have this oxidation effect. Now, the release of the microcapsules was studied in all of the pH solutions, and on the left, we can see that over time, over the 350 hours, for this slower release, that at the two values above the pKa value that we discussed earlier, 7.2, so our simulated concrete pore solution and our carbonate buffer solution of pH 12.6 and pH 9.1 respectively, that we see a much higher release of the corrosion inhibitor. This was performed by the Grice method of binding the nitrite molecules to a dye to see with the UV vis, and it was found that that the release was able to be modeled by the Ricker and Peppa's power law release model for the spherical particles, and we found good correlation there to be able to predict how much inhibitor we can release from these microcapsules over the long term. In terms of the kind of the most important part with the polarization studies and the EIS studies to show the effectiveness of the microcapsules, they were exposed for 7 days in the different pH solutions to allow for sufficient inhibitor to be able to see a major inhibition effect. And what we see is from left to right, we have our low to high pH, and in blue, we have all of our microcapsules. Red are the free sodium nitrite inhibitors, non-encapsulated in the same system, and our black is our control, all in a low chloride, 0.4 weight % chloride solution as the maximum, widely held maximum allowed amount of chloride in concrete, in the concrete mortar or matrix. And we see that the microcapsules, although showing a more active E-cores in the near neutral and pH 9 solutions, do show similar corrosion current densities and values to our free inhibitor solution. And lastly, in our alkaline solution, our simulated concrete pore solution, we see the most ennoblement by the microcapsules, showing comparable E-core values to our free inhibitors, as well as lower I-core and lower current densities in general. and by EIS as well to corroborate the our DC method. We see that in the same color scheme, red being our free inhibitor, our free inhibitor samples showing the most resistance for our 2 lower pH values. However, in our most alkaline, where we will have the most release of corrosion inhibitors, that we then have the greatest impedance in blue here. These are all modeled to our electrical equivalent circuit shown here, are widely used for inhibitors in concrete with 2 time constants, with one for our passive film formation of our oxyhydroxide and passive oxide layers, and our double layer and charge control. And on the left are calculated RP values from the EIS for the simulated concrete porous solution, as that is the major focus, to see that the microcapsules over time, over a 30-day period, we see the polarization resistance values of the microcapsule showing higher even than our free inhibitors, even with comparable nitrate concentrations, likely also attributed by any effects of the colophony, as well as the release of the corrosion inhibitors themselves. As well as to kind of wrap this whole idea up, we have XPS results showing the formation of our passive oxide films. So on the left here is our XPS spectra for iron. In our lower pH, we find that our Fe3+ is lower than our Fe2+ peaks in the deconvolution, showing that there is most likely the corrosion occurring in the formation of iron chlorides and dissolution. However, at the higher pH, the ratio of our Fe3+ to 2+ is much higher, and because of the presence of nitrates, that can evidence the formation of the passive oxyhydroxide passive layer, as well as the Fe2O or Fe3O4, the stable ferric oxide layers. And a schematic of the system showing here is just that at our lower pH values, some inhibitor is released, but we have evidence that it's a low amount, showing that the corrosion will still take place. However, at the alkaline solutions, we see the release of our corrosion inhibitors. This can be beneficial. And lastly, this was beneficial due to during the concrete curing stage, these microcapsules will be able to withhold the corrosion inhibitor solutions. And then as the pH of the concrete mixture increases, we have a release of our corrosion inhibitors, which will effectively be able to diminish the amount of any leaching and premature binding during the initial stages, and allow for the more effective use of our inhibitors and less loss. Again, here's a schematic. And I would like to thank the university for all its funding, and thank you all for having me here and for your attention.
Okay, thank you, Jacob, for your presentation. And we have a question from Sahed Jelinka. So Sahed, you want to go ahead live and ask yourself the question?
Thank you for the presentation. So my question is that what is the benefit of capsulation? Why not directly adding the inhibitor into the concrete, or what the electrolyte you are working on?
That's a good question. So actually, these microcapsules have multiple benefits to just the free inhibitors. So in the concrete environment, we do see that it gives even greater performance in the alkaline solutions. And as well, previous studies by Canovas et al. That I cited at the beginning of the presentation show that the addition of colophony and pine resin into the concrete mixtures itself can decrease the water absorption by the concrete. It can increase the compression and flexural forces and other mechanical properties of the concrete. So, and in addition, we have a possible future study effect of the oxygen scavenging of the colophony itself, that in all of these effects mixed together, we have a kind of a greater effectiveness than just the free inhibitor by itself.
Okay, let me add 3 important facts. So in addition to the oxygen scavenger, of course, and all these improvement on the mechanical properties, the main motivation is that we avoid reaction with the matrix at an early stage. Okay, this is a hydrophobic shell, so it's not going to dissolve in water, and it's not going to react with the concrete matrix. Secondly, we avoid leaching, and third one, we will have a long-lasting effect. So we don't need the corrosion inhibitor to be acting on the early stages. Okay, not sure if we clarify on that, Sahed. Can you confirm? Okay, I'm assuming it's fine. All right. Any other questions or comments?
Hi, David. This is Burkan.
Okay, sure.
Maybe I should refer my question to the presenter, but I understand the time release is important. Have you looked at how long it takes for all the inhibitor to be released from the system?
Yeah, as of right now,
so
we haven't gotten to 100%. No.
Okay.
Right. And we're not. It's not certain that it will reach 100%, as the model would predict that it would plateau earlier before 100% would be released.
But regardless, these are relatively short times, right? We're talking about 350 hours. So with that time release concept, are there any efforts to slow that process further?
As of right now, we're looking into the modifying of the microcapsules to be able to adjust the release, but nothing more in depth than that.
Okay, thank you.
Let me add on that, Jacob. Your results are on simulated concrete pour solution.
Yeah, right? Yeah. These are all simulated.
Those are accelerated tests. Okay, we haven't yet tested on a real concrete, neither mortar. So that might be answering. But I mean, you have roughly time for that threshold. Is that right, Jacob?
Yeah.
Can you elaborate on that, please?
Yeah. So it would appear that by the models itself, we would get to a plateau for our simulated pour solution of about 65% by the power law model of the total inhibitor released. So we won't get the full 100%, but we'll still have the added effect of the colophony shell itself.
So probably the target here is to get to the point where we can control the release at least for 28 days, what is supposed to be the curing time. Okay, that's the target. I don't know if we answer your question, Burkan.
Yeah, you did. I think it would be nice to look at that time effect in concrete or mortar for sure. But the goal here is to achieve release around 28 days. That's what you're saying, David.
Okay. Thank you so much for interesting question. We have another question of Mabubet Ate. Mabubet, do you want to go live?
Yeah. Hello. My question is the effect of the polymer by itself. When we add, imagine if we add just this polymer as a shell to the concrete, do you study this effect? Is colophony by itself has any effect to increase the resistance or to improve the corrosion?
So the colophony shell as a microcapsule in that shape and form has not been studied in the concrete, but the colophony as a powder mixed into the concrete matrix has been studied by Canovas, and they found that it does decrease the water absorption and the porosity, as well as increase the mechanical effects. But in terms of corrosion, that's in the corrosion in actual concrete, as we have not studied that, no.
Okay. Because probably we can separate these two effects.
Yeah, definitely.
Okay, thank you.
Jacob, can you elaborate on the oxygen scavenger effect of the colophony?
Yeah, so we see in all of these simulated solutions that the oxidation of colophony, at least it does occur in the way that Ren et al. Described in their paper. And with this mechanism here from abiotic acid on the left to the oxidized form on the right. And so this, in effect, would be using up a lot of, using up the oxygen that we have in our system so that any oxygen, if we have some of this polymer absorbing to the surface, the oxygen that would come to the surface of the rebar would then be scavenged by the colophony polymer and then oxidized of the colophony instead of participating in the corrosion reaction. So in that effect, we would have like a cathodic inhibition from our colophony itself. So we have evidence for that, but we don't have that in actual concrete so far.
Okay, so thank you so much, Jacob, for a great presentation, and big applause for you. So finally, we'll move to our last presentation, but not least. This is a pre-recorded presentation, so I encourage you to stay. And this is by Rutambara, Sonawane from Florida International University. So please, Cedric, go ahead and activate the presentation.
Hello, everyone. Thank you for joining this online presentation today. I am Rutambara Sonawane, a PhD student at Florida International University. My co-authors are Dr. Samanbar Parme and Dr. Kingsley Lau. My topic is development of deficient grout and corrosion due to water and solute transport. This is basic introduction. Pre-stressing is the process of introducing stress into a concrete element by tensioning high-strength reinforcing steel. There are two types of pre-stressing system. One is pre-tensioning and another one is post-tensioning. In post-tensioning system, the strand tension after placing of the concrete and the remaining space into ducts is filled with the grout. Grout is a cementitious material which protects steel from corrosion as the pore water of the grout has alkaline pH which allows the steel to passivate. There have been many corrosion failures of bridges documented in past 30 years. Therefore, there have been many revisions in the grout material and construction specifications. Before 1990s, corrosion was related to moisture and chloride ion, and after 1990, corrosion attributed to improper duct filling with voids due to development of grout bleed water. In 2000, anti-bleed thixotropic grouts were developed, but still corrosion cases were observed. On right hand side, you can see these are the corroded tendons. The bottom one is a ringling bridge tendon. Ringling bridge is one of the example of these kind of failures. Corrosion failure of tendons was identified in 2011 in the bridge of Florida after only 8 years of service. More than 10% of external tendons were replaced. In 2013, investigation of the cause showed that failure of post-tension tendons utilizing updated thixotropic grout products. This corrosion was not directly associated with grout voids, bleed water, or chloride, but the corrosion was related with physically and chemically deficient segregated grout, which is moisture rich with high concentration of sulfate and alkali ions. The total chloride content in the deficient grout was low to moderate, and the pH of segregated grout was typically greater than 12. Rather, the deficient grout had high moisture content and elevated sulfate concentrations. Strand in the location of the tendon failure exhibited severe corrosion mostly concentrated in the upper portion of the tendon cross-section. In these pictures, you can see the segregation of grout. Grout at high elevation, that is soft grout, had high sulfate ion, low chloride, high moisture content, and high pH. The first picture we can see weight segregated plastic grout, and this pink color shows it is a phenolphthalein indicator spread on grout, and it shows pink color that is indicator of high pH. In 2011, Bertolini and Cassana reported that segregation of injection cement grout for pre-stressing cable may lead to the formation of whitish phase with a plastic consistency characterized by high content of alkali and sulfate ions. In 2016, Samanbar Parme reported that water content of hardened grout with sedimented silica, here you can see here, it's approximately 20% by mass, but at higher elevation, the water content exceeded by 60% by mass and having a weight and plastic consistency, and 50% of grout was soft and chalky. Here are the XRF and XRD data compiled relating to sulfur containing compounds as shown in these graphs. This is XRF and this is XRD. Here we can see the gypsum and ettringite. High sulfate concentrations was measured in the grout pore water and was further supported by the identification of ettringite in the macro pores of segregated grout. Gypsum and ettringite identified as sulfur-bearing crystalline compounds. These black data shows the actual breach sample data. At the top of the sulfur is more than the bottom one. In this slide, we can relate sulfate content to the moisture content. The moisture content of deficient grout can exceed 20% by mass, and moisture in hardened grout, as expected, was lower. These triangular symbols shows values from the breaches where corrosion failure occurred. High chloride found in some breaches, but it was unrelated to the segregation of grout, as chloride content was same in hard and soft grout. Deficient grout shows higher moisture content and free sulfate concentrations, and even corrosion was observed in deficient grout, with widely variable low end limits of free sulfate values. This is large-scale laboratory mock-up test. Modified incline tube test includes pumping of grout within a duct that is 3-inch diameter here and 15 feet long PVC pipes, which is placed at an angle of 30-degree inclined. The grout material is pumped from bottom, and the valves at the outlet and inlet were closed sequentially to prevent loss of material. As per research by Hamilton and Parme, the top elevation showed that the moisture content was greater than 20% and sulfate level was elevated. These research efforts show that this stage setup can elevate the formation of deficient grout at the upper elevation of the tendon. MIT can facilitate grout deficiency shown by differentiation in moisture from upper and lower elevation. These MIT samples were casted using excess amount of water as shown in last slide. These are the results from moisture content and the pH. Here we can see normally higher pH maintained in deficient grout. This is deficient and this is hardened grout. And moisture content is also much higher in deficient grout. This is hardened grout. Sulfate ion and other chemical species were tested. Grout was collected from the middle of MIT sample pipe where grout was hardened and near to the high elevation pipe cap where grout was segregated. Elevation of potassium sulfate and chloride um, was observed in higher portion where grout was segregated. And chloride content remained low. As described by others, the enhanced alkali content may be important in the development of high pore water pH. These are results of electrochemical testings. This one is corrosion potential and another one is current density. In the first corrosion potential, the deficient grout in the upper duct elevation had more distinct differentiation of negative active potential, and in current density, corrosion in the current density for the steel embedded in deficient grout in the upper elevation of specimen were consistently and distinctly higher than the hardened grout that form in the lower elevation of the specimens. In the presence of deficient grout that enhance corrosion, more electronegative potential and higher current density in deficient grout. It is possible that the transport of water and ions are related to the development of grout deficiencies, in part relating to hydrostatic pressure. These are other related factors in segregated grout. Water content. In hardened grout, we had 20% water content. Segregated grout, it was up to 85%, and variable grout porosity in hardened grout nearly 20%, and segregated grout has lower cement content. In these pictures, you can see the wet plastic grout has large porosity than the hardened grout. In 2002, Schupak stated that the grout in a taller duct will experience larger hydrostatic pressure. These all factors can affect the water retention characteristics of the grout. To model this transport of porous media, we can use Hydrus 1D. Water retention curve is the base of this modeling software. This is pressure head versus moisture content. As we can take out water from saturated media, it goes to negative potential. Therefore, it can go to minus infinity. It can numerically solve using Richard's equation for the solute transport, which can be used in unsaturated flow. This is Van Genegten equation. KH is unsaturated hydraulic conductivity. To get that, we can use saturated hydraulic conductivity. This is degree of saturation formula, where theta R is a retention water content, theta S is saturated water content, alpha M and N are retention function. This is summary and future work of this project. Segregate grout has high moisture content and elevated sulfate ion concentration in the pore water. Due to this, steel corrosion was elevated. MIT can facilitate grout deficiency by differentiation in moisture from upper and lower elevation, where tests shows differentiation of moisture content, sulfate ions, and physical grout characteristics. Implementation of modeling using Hydrus 1D to consider deficient grout characteristics in progress to identify transport mechanism. These are the references. Thank you.
Thank you so much, Rutambara, for a great presentation. I can see you now online, so you'll take question live. And now floor is open for questions, so please go ahead and ask.
Well, if she is able to respond, David.
Rutambara, she's live.
Okay,
yeah.
I wonder if she knows the work from Ivan Lassa in Florida, because they have studied this problem, and they were identifying the sulfates as the passivating ions for the corrosion. I wonder if you like to extend a bit more on that.
Hi, Dr. Andrade. This is Kingsley. I'm her major advisor. Indeed, the research was stemming from was sponsored by FDOT with Ivan Lassa, and the work is coming from that. We have a project, and it's extenuating, trying to find test methods to identify sulfates and identifying the causes for deficient grout. So what Rutambara is working on now is trying to develop the mechanisms and the transport mechanisms why the sulfate accumulate. Yeah, but Ivan has been our project manager for the past couple of projects, and we're definitely appreciative of their support.
Yeah. And also, if you know where the sulfates, I mean, is the normal amount of sulfates in the cement, does it comes from the gypsum that is added to the cement, or is an addition that they put into the grout?
That's a very important question for us for a very long time. Our early results show that with these commercially available grout products, you're able to accumulate sulfate ions without external contamination. So it seems like whatever is able to dissolve the sulfate is coming from the materials within the grout itself. Of course, these are commercialized products, and so we're not privy to knowing all the exact contents inside. But you can accumulate without the presence of external contamination. The causes of the root causes for the Andrade or the gypsum to go into solution, that's something that we're still working on. We have suspicion that that some of the sulfate ions may be coming from kiln dust, because the reason we see, especially in the field testing from a few years ago, we always see elevated alkalis with elevated sulfates. So we feel there may be some kiln dust in terms of potassium or sodium sulfate that's in the system. But that's something that we're still trying to understand and determine how is it that's going into solution and accumulating.
Thank you, Kingsley, for clarifying on that. I don't see any other questions, so I'll go for just a comment. I saw in one of your plots that you were showing some presence of NO2 and NO3 in addition to the sulfates. And my question will be, do you experience any reduction on the corrosion that could be attributed to this NO2, NO3? What is your impression on this content?
Yeah, those are important questions too. The data we got from essentially with the NO2 and NO3 came from testing from the original bridge site, and at that time we were very limited in the amount of material we could get because it's basically coming from a field site. In the subsequent testing, we were not able to get large quantities of that, and the biggest reason why is because through all the lab testing, we were never truly able to reproduce what occurred in the field site. That level of segregation was very severe, and a lot of it has to do with the size factor and the construction that went on the actual bridge site. As much as we try to simulate in the laboratory, even large-scale testing, we were never able to really get that degree of grout deficiencies, and so we were not necessarily able to get those levels of the chemicals as well. Something that we need to look at and continue to do so.
Okay, thank you so much, Kingsley. And again, thank you for a beautiful job and nice presentation. So big applause for you. And that will conclude our session. So again, thank you everyone, all the speakers, for a wonderful presentation, good scientific level, by the way, and I acknowledge that. And also to the participants for your patience. So we're running late of time, but everyone was very kind to continue attending our presentation. Finally, but not least, I would like to acknowledge MDPI, and in particular to Professor Digby McDonald, Raman Singh, and Reese John for such a great initiative to organize this remote conference. I hope we can do that next year and in future years. Thank you so much again, everyone, and have a wonderful time. Be well. Thank you.